Like this is page, look here in your book, page 259, number 22. And it's a hungry bear that's trying to get some goodies at the end, and he's 700 newtons. The beam is uniform, and it's 200 newtons. It's 6 meters long, and the goodies are 80 newtons. And they want to know, first of all, A, they want you to draw a free body diagram of the beam. And then B, they want to find what the tension in the wire is if the bear makes it to 1 meter. So, I'll move this down just a little bit. So basically I've got a pivot point right here. I can put my pivot point wherever I want, but it naturally is right here. That's going to be easier to deal with. And so at 1 meter, I've got my bear. So distance from there to there is 1 meter. He is 700 newtons. That's his weight. Then right in the middle is where the force of the beam acts. So from there to there is going to be 3 meters. I know that because this is, if this is 0, it's a 6 meter long beam, right? And then right out here at the end, I forgot, sorry. This is 200 Newton beam. That's its weight. And then out here at the end, I've got 80 newtons. And then also at 6 meters, I got the tension in this cable at a 60-degree angle. So, distance from here to here is obviously 6.0 meters. So here's how we do a problem like this. I've got all the forces on there and the distance from the pivot point to each force. And we know that torque equals force times the distance from the pivot point to where the force acts times the sine of the angle. Remember, sine of 90 is 1, so if they're 90 degrees, like these guys right here, all three of these are 90 degrees, then I don't have to use sine because sine of 90 degrees is 1. This one's 60 degrees, though, so I'm going to have to use sine here. And what we do is we say that the clockwise torques will have to equal the counterclockwise torques. Well, if I look, I have 3 forces that are attempting to make this beam rotate in a clockwise manner. And then I got 1 force, the tension in this cable, attempting to resist that. They're resisting that in the counterclockwise. So I'm going to take, and torque is force times radius times sine of theta. So I'm going to take each of these forces and multiply by the distance away. And so to do that, it's going to be 700 newtons times 1 meter plus 200 newtons times 3 meters plus 80 newtons times 6 meters has to equal the counterclockwise torque, which is the tension, I don't know it, times 6 meters times sine of 60 degrees. All right, so that's going to be what, 700 Newton meters plus 600 Newton meters plus 80 times 6 is 480 plus 480 Newton meters has to equal, see, sine of 60 times 6 meters is 5.2. 5.2 times the tension. All right, if I add those 3 together, those 3 torques, I get 1780 over here on this side. Newton meters equals 5.2 times T, divide both sides by 5.2, and I get 342. So 342 newtons must be my tension to counteract all that. So this is the answer to A. And this is the answer to B. And then the last part, they say if the wire can withstand a maximum tension of 900 newtons, what's the maximum distance the bear can walk? The only difference, you're doing the same thing, except now you know this number right here. This is for the C part. This number right here, you know, is 900 newtons. That's the maximum. And you don't know this number here, the X. See the X value? That's what you're looking for. So I want you guys to go try to set this up and see if you can find X, distance X. And you should get a maximum of 5.14 newtons if you do it right. So that's it. That's how you do a problem that's a static problem